So this is the last lecture. There's no, if you come here on Friday, you won't, you might be the only ones. There's no class on Friday for this class. Okay, so we're going to do an example. Kind of a real-world example, well, maybe a bit artificial though, about absorbing Markov chains. Okay, so let's do an example where it's basically going to be some kind of situation where you own a stock, and the stock price can go up, the stock price can go down with certain probabilities, and you want to, you're going to sell the stock at some point, and we want to know if you're likely to make money or lose money. So let's say you own shares in a stock that is currently valued at $1. Okay. And when you have like stocks, you can set up like an automatic thing on your account to sell it at a certain price. So let's say that you set up your account to automatically sell all your shares if the price reaches 98 cents or $1.02. Okay, so basically, like maybe you're worried about the price going way down, so you're like, okay, if it hits 98 cents, let's just like stop it there and sell it. And then maybe you're like, okay, if it hits $1.02, then I'm going to lock in my profits. I made 2%. Let's lock it in and sell it. Right? I don't know. Okay, but this stock has some kind of interesting behavior where, so each second, so like stocks update all the time their prices. So let's say in each second, the stock price changes randomly. In the following way. Okay, so if the price is $1 at some time, so for example, at the beginning, it's $1. It has a 0.4 probability of going to 99 cents, and then a 0.6 probability of going up to $1.01. So it's always going to change. So in every second, it changes by exactly like 1 cent, either up or down. Okay. So if it is at 99 cents, then it's going to go down to 98 cents with a 10% probability. So it goes to 98 cents with probability 0.1, and it goes up to $1 with probability 0.9. Okay. And the last thing is, if it is $1.01 currently, then it goes up with a, so it goes to $1.02 with probability 'kay, I'm going to switch from decimals to fractions here. So 1/15, and then to 1, it goes back to $1 with probability 14/15. Okay, so sorry, that's a lot of writing. So basically the question is, what is the probability that the price is $1.02 when you sell? Okay, because it's either going to be $1.02 or 98 cents, and yeah. Okay, so sorry, this is a lot of, that's why I kind of hate the word problems in this course. There's always a lot of writing, but yeah. Any questions about the setup here? So you got stock, it starts at $1, it goes up, it goes down, you know, with different probabilities. And if it hits one of these values, you automatically sell, and then we want to know what's the probability you make money, what's the probability you lose money. And hopefully, I don't know, from this information, to me it's not clear what the answer is, if you're more likely to make money or lose money. Actually, let's maybe have a vote. Maybe thumbs up or thumbs down. So thumbs up if you think that it's more likely to make money from this stock, or thumbs down if it's more likely to lose money from this stock. And if it's not clear to you, well, it probably shouldn't be, because it is a really weirdly complicated problem, right? So like initially you've got it's $1, right? You do have a higher chance of going up at that point to $1.01. That looks good. But once you get to $1.01, you've got a really high chance of going right back down to $1. And then if you go down to 99 cents, you have a very high chance of going right back up to $1 again. So it's going to really be in that middle area for a long time, probably. Yeah. Okay, I'm not sure what the majority was there, but yeah. We'll see what happens. Okay, so I want to think of this as an absorbing Markov chain. Actually, can anyone tell me what, if I wanted to think of this as an absorbing Markov chain, what are my absorbing states going to be, probably? Yeah? Yeah, exactly, because, you know, yeah, so to repeat that louder, 98 cents and $1.02, right? Because if you ever reach those values, then your value can never change, right? Because you sell the stock, you lock it in. So like if you think about it updating every second, if you ever get to $1.02, then the next, you've sold the stock, and now so for the next second, a second later you have $1.02 forever because you sold it, right? So yeah, this is an absorbing Markov chain with your absorbing states being 98 cents and $1.02. So let me kind of draw a transition diagram here. So it's going to look something like this. So your states are the different amounts of money. So I've got like a 60% chance, which is the same as 3 over 5, of going from $1 to $1.01. I've got a 40% chance, which is the same as 2 over 5. If I'm at $1, those are the two things that can happen. Here I've got like a, so I'll just call it 9 over 10. 1 over 10. Here, this is our absorbing state. Once you get to 98 cents, you can never leave that state. And here I've got like a 14 over 15, 1 over 15, and 1 like this. Okay. Does anyone want to change their, now that they've seen the picture, like change your vote? Do you think we're going to make money or lose money? I don't know. Okay, so let's start analyzing this. So, so remember we had this kind of multiple step procedure. Well, actually, maybe even before anything here, we need to kind of write down a matrix with our states. And remember, kind of the first step last time was to like organize your states so that the absorbing states come first. Okay, in this case, we can just do that right from the beginning because we don't even have a matrix yet. So we can just make our matrix have that property. So I'm going to list my states as 98 cents, $1.02, and then, so these are my absorbing states, 99 cents, $1, $1.01. So I'm just drawing the transition probabilities, the transition matrix. So, right, we want our absorbing states first. Okay, and we need whatever order we pick here, we should pick the same order for the columns. Okay, now we can write in our probabilities. So oh, by the way, hopefully it's clear that this is an absorbing Markov chain, right? Because actually every state, like from any non-absorbing state, you can get to both absorbing states. So it's definitely an absorbing Markov chain. Okay. So what we want to do is find the limiting matrix. Okay, so here are our transition probabilities, right? Okay, now what about for this one? So if you're at 99 cents, you have a 1 over 10 chance of going down to 98 cents. There's no way to go, you only go up and down by 1 cent each time, so there's no way to do this. It's kind of a strange stock in the sense that there's no way for the price to even stay the same, which let's just go with it. So then you've got a 90% chance of going up to $1, 0% chance of going all the way up to $1.01, and so on. So oops. Okay. Is everyone okay with these values, or are there any questions about that? So each value here, like if I'm in this state, this number corresponds to the probability of moving from that state to that state. And that just comes from the statement of the problem, right? And all these rows add up to 1, so like it looks good. Okay, so now we do this thing where we break up the matrix into these quadrants. So we think of this as like I for the identity matrix, and then 0 because all of these are zeros. We call this R, and we call that Q. Okay. Notice that I think last time we had the same number of absorbing and non-absorbing states, like there was 2 of each. And so this was like a 2-by-2 matrix, but in this case we've got 3 non-absorbing states and 2 absorbing states. So this is not a square matrix, but that's okay. There's nothing wrong with that. So in this picture, like this one should always be a square matrix, where it's like the number of absorbing states by the number of absorbing states. This one should always be a square matrix, because it's like the number of non-absorbing by the number of absorbing. Sorry, non-absorbing. But this is not going to be this might not be square, but that's fine. Any questions about this? So this is just finding the right way to divide up the matrix. Does anyone remember, well, okay, maybe this is hard question to ask, but right, so if this is your transition matrix and it's an absorbing Markov chain, then we had this key fact from last time that your limiting matrix is going to look like this, right? Does anyone remember what goes here? Yeah. Yeah. So yeah, just to kind of say that again, so yeah, I minus Q inverse and then times R. Okay. I still don't have a great justification for why this is the case. And actually, I was thinking about how I would justify it yesterday, and it's probably a little bit beyond the level of this course, but yeah. But that is what you really should get there. Okay, so what we need to do is compute this matrix, and then we plug it in, and then that's pretty much the end. We just have to interpret it after that. Okay, don't forget, if you want to give feedback on the course, there's a course experience survey. Okay, so I want to compute I minus Q inverse times R. That's a lot of stuff, a lot of steps. So let's just do them one step at a time. So first, let's just write down what is I minus Q. So first of all, what is I? I is the identity matrix, and we're always going to pick it to have the right size. So it should be the same size as Q. And Q is 3 by 3, so the matrix I will be a 3 by 3 identity matrix. And then we subtract Q. Right, so that'll give us the matrix 1, negative 9 over 10, 0, negative 2 over 5, 1, negative 3 over 5. and then 0, negative 14 over 15, 1. Okay. But that's not quite the right thing, right? We don't want I minus q. We want I minus q inverse. So let's get the inverse of this thing. So last time I kind of skipped this step, but this time let's just do it for real. You guys need to have practice with Gauss-Jordan elimination. So let's do a complicated example. So always when you're trying to find the inverse, so this is I minus q, we want to get the inverse, right? So what you want to do is throw this into I guess they call this like an augmented matrix, like a matrix where on one side you put your original matrix, then on the other side you put the identity. Okay. And then we want to do Gauss-Jordan to this. Okay. So I'll go through all the steps, but I might, I might do some of the calculations quickly, but feel free to slow me down if you want, if you have questions. So, all right, so we're trying to get first column 1, 0, 0. We got our 1. We want to do row 2 plus 2 over 5 row 1. Right, standard thing, you want to get rid of that negative 2 over 5, right? And if you do the calculation, so this row doesn't change. This row becomes 0, 16 over 25, negative 3 over 5. Here I get a 2/5, 1, 0. The bottom row doesn't change either. Right. Okay, now I'd like to get a 1 here, right? So I'm going to divide by the appropriate thing. Yeah. Yeah, that should, oh, no, that, yeah, that's still negative 3 over 5 because I'm just subtracting like 0 or adding 0 to it. Yeah. Yeah, but usually those numbers would change, but yeah. Because it was a 0, it's okay. Yeah, so I'm going to now kind of make that a 1. So just multiply that row by 25 over 16. Right? Whatever number you see there, just multiply by like 1 over that number. That should do it, right? Or flip the fraction upside down. It's the same thing. So I do that to R2. This thing becomes negative 15 over 16. If you do the calculation, that becomes 5 over 8, 25 over 16, and then 0 still. And third row doesn't change. Okay, so now I'm going to completely sort out the middle column, add 9 over 10, so row 1 plus 9 over 10, row 2, row 3 plus 14 over 15, row 2. Okay. This is always the procedure, right? You get your 1 by just dividing a row. Then you clear out everything else by taking that 1 and adding it, appropriate multiples of it to the other things, adding or subtracting. Okay, so this column's still 1, 0, 0. Now this column is happy. It's 0, 1, 0. Everything else gets more complicated. So this is like negative 27 over 32 if you compute it. Oh, maybe I'll give myself more room here. This is still negative 15 over 16, and that'll be 1 over 8. So none of these actual numbers should be obvious because, yeah, I don't know. I'm doing a lot of calculations and not really showing you where it comes from, but this, this negative 27 over 32 comes from, like, it's 0 plus 9 over 10 times negative 15 over 16 is where that comes from. Okay, and over here we've got 25 over 16, 45 over 32, 0. We've got 5 over 8, 25 over 16, 0. Same as before. And here we've got 7 over 12, 35 over 24, and 1. Only 2 more steps here. Okay. Okay. I'd like to get rid of that 1 over 8. Let's just multiply the row. Right? So 8 times row 3. So everything else is the same. Zero, 1, negative 15 over 16, 5 over 8, 25 over 16. So for the first 2 rows, I'm just copying what I had before. And for the last row, it should be 0, 0, 1, 14 over 3. Apologies for all the nasty fractions here. 35 over 3, or sorry, 35 over 24. No, sorry, over 3. And then 8. Okay. So sorry, I'm kind of going through this pretty fast, but if you needed to reproduce this, you'd have the, you could pause the video or something. So right now we're just gonna wipe out everything else in this column. So row 1 plus 27 over 32, row 3. Row 2 plus 15 over 16, row 3. Okay, so this is, we're actually done now. The last thing is just writing these numbers down. This becomes 11 over 2, 45 over 4, 27 over 4, and then 5, 25 over 2, 15 over 2, and then 14 over 3, 35 over 3, and 8. Okay. Then after all of that, we just have to remember what the heck we were trying to do. We were trying to find the inverse. And so like this is, that matrix there is the inverse, right? If you wanted to check it, you could always multiply, take that matrix here and multiply it by this matrix, and you should get the identity. But you don't have to do that. It's just if you want to check your answer. OK. So yeah, so sorry for going through that quite quickly, but yeah, hopefully the procedure is clear, right? We've done a lot of Gauss-Jordan before. And don't worry, I don't think you'd have anything this complicated on the test. So, OK, so we've got I minus Q inverse, which is almost what we want. What we actually want is that thing times R. So let's just multiply it by R, right? So I minus Q inverse times R is 11 over 2. So I'm just writing the matrix again, 45 over 4, 27 over 4, 5, 25 over 2, 15 over 2, 14 over 3, 35 over 3, 8. So this is just I minus Q inverse. And R is 1 over 10, 0, 0, 0, 0, 1 over 15. If you're wondering where that R came from, it's this, right? OK, so the R just comes from the bottom left corner, the bottom left quadrant when you do this splitting, right? OK, so matrix multiplication. This is actually a pretty easy matrix multiplication because I've got a lot of zeros over here. That's kind of helpful. But generally speaking, what you do is you take this number times this number plus this times this plus this times this, right? And that gives you the entry in the first row, first column. So this is 3 by 3. Yeah, so this is going to be 3 by 2 in the end. Right, so if you want the first row, first column, you take the first row of this, first column of this, right? First row times first column, multiply them up and add them. In this case, it's only, you only really have this term, so it should be 11 over 20. Yeah. When you want to find the next thing, so the first row, second column, I take my first row here and multiply it down the second column here. So you can do that calculation, but actually I kind of already know the answer. So as it turns out, like the things on each row of this, like I minus Q inverse times R, everything on this row it's got to add up to 1. Because, well, so in the limiting matrix, every row adds up to 1. And you know that everything over here is 0. So everything in here has to add up to 1. So actually, like, I can, since I know there's only 2 kind of columns here, I know that that's going to be 9 over 20. Because, yeah, it's got to add up to 1. It just makes my life, like, it saves me about 2 seconds, like, or maybe 5 seconds to not have to compute that, right? But then I spent 20 seconds talking about it. OK, so for the next one, 5 times 1 over 10, and then this stuff times 0. So it's a half, which means this has to be a half. If you check, this is 7 over 15. So that has to be 8 over 15. OK. So now finally, So I can now just write down my limiting matrix. For this, we should remember which order we put our states. So I'm going to write them again: 98 cents, $1.02. Because like we're going to need to interpret some stuff here. So and the order we put these things, it was kind of a strange order, right? So we should remember what it was. Okay, so the limiting matrix, I'm just going to copy what I see here. So that should be the identity. This should all be zeros. This should all be zeros. Okay, and then I just copy the values from that thingy over there. So, right, so 11 over 20, 9 over 20, and you can see it's the right size, right? So 9 over 20, 1/2, 1/2, 7 over 15, 8 over 15. So now if we want to interpret this, it means that actually everyone who answered the question, like that you're more likely to have 98 cents or $1.02. So it was kind of a trick question. You're both wrong. Because actually neither is most, or maybe you're both right. I don't know. Neither is most likely because, so if you start with $1, what this says is that you have a 50% chance of ending with 98 cents and a 50% chance of $1.02. So actually, they're both the same probability. So basically, if you kind of interpret this, so if you start with $1, you have a 50% chance of ending with, 98 cents or $1.02. Okay, so sorry, that was kind of a trick question. But this also tells you other information, right? So imagine, like, so I know in our question we said we're starting with $1, but if you started with 99 cents, this tells you that this is the chance that you're gonna lose money and end up with 98 cents, and that's the probability you're gonna gain money, right? And you're gonna end up with $1.02. And same if you started with $1.01. These are your two probabilities. Okay. So these are like your long-term probabilities, right? And just to interpret the rest of this matrix, because in case it's not clear, like hopefully these values make sense as well, right? If you start with $1 and you let this Markov chain run for a really, really long time, the chance that you end up with $1 at the end, well, it's going to be 0 because if you think about it, it's really unlikely for the Markov chain to just stay between $1, $1.01, back to $1.99, back to $1. To do this forever, it's eventually going to jump up to one of these two absorbing values. So if you run this for like a million steps, the chances of having $1 after a million steps is really unlikely. So in the long run, it should be 0, right? Also, these things make sense if you start with 98 cents. that'd be kind of a strange thing to do if you buy a stock for 98 cents and say that I will sell it immediately when it gets to 98 cents. Then it's just going to immediately sell it, and you're going to have 98 cents, right? Okay. Any questions about any of this? Or last chance for any questions for the whole course, I think. The test or anything like that. I think it's basically like, I can't exactly remember. It's definitely on Brightspace somewhere, but I think it's like from maybe the end of the matrix stuff up until this, basically. So it also includes linear programming. I think maybe computing inverses, but I'm not exactly sure. But it's on Brightspace somewhere. Yeah. Oh, yeah. So this Markov chain is all in like chapter 6 of the PDF. But looking at the other parts of the PDF are also useful, like for linear programming and stuff like that. But this is just chapter 6. And this specifically, what we did today is the 3rd section of chapter 6. So it's absorbing Markov chains. The 6th, or for the test, you'll have to do the whole 6th chapter of the PDF. Yeah, the handbook. Any other questions?